Software systems often involve immense complexity, with databases, logic, and configurations tangled together. But for a user or developer to interact with them effectively, that complexity must be managed. This is where abstraction comes in. Abstraction is the powerful process of hiding messy, complicated details and showing only what is necessary. It functions almost like a formal contract. But defining an abstract class, a system dictates that any class using it must include specific required methods, without any concern for how those methods are internally programmed. In Python, this is achieved using the built-in ABC module. These abstract classes serve as templates for other classes. They cannot be used to create objects directly, but exist solely to establish rules for their children, ensuring every concrete class follows the same structural blueprint, as you see in this hierarchy on the right. To make this intuitive, consider the experience of driving a car. As a driver, your interface consists of just a few things: a steering wheel, an accelerator, and a brake pedal. These are all the components necessary for operation. You don't see nor do you need to manage the hidden internal complexity of the vehicle. You aren't calculating fuel injection timings, managing ABS pressure, or monitoring engine combustion cycles. All of this is abstracted away from you, securely hidden from the driver. This abstraction provides the driver with a clean and simple interface. The core takeaway is that abstract classes perform this exact same function in code by defining the methods that must exist while completely hiding the implementation details inside each specific subclass. Now that we understand the concept, let's step through exactly how we build this out in Python.
Implementing abstraction in Python follows a specific 5-step process. First, we import ABC and abstract method from the built-in ABC module. Second, we define a class that inherits from ABC, which officially tells Python, hey, this is an abstract class. Third, we use the abstract method decorator to identify the mandatory methods that every single child class must implement. Fourth, we have to ensure all those abstract methods are actually defined in our child classes. If even one is missing, like collect payment is missing here in the bike delivery class, the program will crash with an error when we try to create an object. However, if all mandatory methods are included, like in our truck delivery class, the object can be created without any issues. Finally, remember that you cannot create an object directly from the abstract class itself. If you try, you will get a type error. To make this super intuitive, a useful way to view this is that an abstract class is just a job description, while the child class is the actual employee performing the work. Imagine a job posting pinned to a notice board. This notice represents our abstract class. It lists the requirements for a delivery driver. The applicant must be able to drive a vehicle, navigate a route, and collect payment. Now, you cannot hire the piece of paper on the notice board, right? You must hire a real person or a child class who can actually perform those 3 tasks. You could hire this truck driver or you could hire this bike driver. While one driver might use a truck and another uses a bike, the specific how or the implementation detail does not change the fact that they both fulfill the exact contract required by the job posting. In the next section, we will see how this contract-based approach provides incredible flexibility when working with different systems.
In IT and cloud computing, abstraction allows for incredible flexibility, letting us design systems that are robust yet easy to adapt. Consider a company using 3 different cloud providers: AWS, Azure, and GCP. Instead of writing unique, tangled code for each individual provider, they create one abstract class called Cloud Storage. This class forces every provider to implement 4 standard methods: upload, download, delete, and list files. Consequently, the main application code only interacts with this single cloud storage interface. Because the specific messy details of the cloud provider are abstracted away behind the scenes, switching from one provider to another requires changing only a single line of code. This isn't just theory, it is how massive systems operate. For instance, Apache Kafka, a tool used by major platforms like Zomato, Flipkart, and Swiggy for real-time data streaming, relies heavily on abstract classes. It uses a base abstract consumer class. This class mandates that any specific consumer implementation must include three methods: poll to fetch messages, commit to confirm processing, and close for a clean shutdown. Whether an engineer is writing a consumer for JSON, Avro, or protobuf data formats, they must follow this exact same contract. This ensures the underlying streaming infrastructure remains absolutely stable and does not need to change regardless of the data format being processed. In the provided Python code on the right, we begin by importing ABC and abstract method from the ABC module. We then define the cloud storage class inheriting from ABC. Within this class, the init method is used to store a bucket name, showing that abstract classes can indeed have regular initialization logic. However, the methods upload, download, and delete are marked with abstract method decorator and contain only the pass keyword. This signifies that these methods have no logic here. They are simply placeholders that must be filled by any child class. Additionally, the class includes a concrete or regular method called showBucket. Unlike the abstract methods, this method contains actual code that all child classes will inherit and use without needing to rewrite a single line. Now let's look at the implementation. The code defines three child classes down here: AWS Storage, Azure Storage, and GCP Storage. Each of these inherits from cloud storage. To satisfy our abstract contract, each class provides its own specific logic for those required methods. For instance, when AWS Storage calls upload, it prints a message specific to AWS S3. When Azure Storage calls the same method, it prints a message regarding Azure blobs. Despite these different internal behaviors, they all share the exact same method names and signatures defined by the parent abstract class. The code demonstrates the sheer power of abstraction through this backup files function. This function accepts an object of type cloud storage. Because of abstraction, this function can call storage.upload without needing to know if the storage object is AWS, Azure, or GCP. When tested, passing an AWS object results in AWS-specific output, while passing an Azure object results in Azure-specific output using the exact same function logic. Finally, the code notes two critical failure points. Attempting to create an object directly from the abstract cloud storage class will cause a type error, and creating a child class, like this bad storage example, that forgets to implement a required method like delete, will also result in a crash. To really solidify this, let's explore some specific questions about how this compares to just raising a not implemented error and how we might model a multi-bank payment system.
To deepen your understanding, let's break down these key concepts visually. First, let's compare an abstract method to a regular method that simply raises a not implemented error. While they might seem similar at first glance, abstract methods provide a much stronger safety net. Why? Because they completely prevent the object from being created at all if a required method is missing. On the other hand, a regular method raising an error will only crash later when the code is actually executed at runtime. Catching errors during object creation is always safer. Second, imagine building a multi-bank payment system. You would define an abstract bank class that establishes the rules requiring essential methods like check balance, transfer funds, and authenticate user. This ensures that, regardless of whether you're dealing with HDFC, ICICI, or SBI, every single bank guarantees exactly these standard operations. Third, remember that abstract classes aren't limited to just enforcing missing methods. They can also hold concrete methods directly. For example, a method like showBucket can be fully implemented in the abstract class. This is incredibly useful for providing shared functionality, things like logging or basic data formatting, which is then inherited for free by all the specific banks, saving you from writing the exact same code repeatedly. Now let's look at a practice problem. You are tasked with designing an abstract class called report generator for a business intelligence tool, like one DMART might use. This class must define three core abstract methods: fetch data, process data, and export. Once that framework is in place, you should create concrete child classes, namely sales report, inventory report, and HR report, each implementing these three methods with their own specific business logic. To test this entire design, you'll write a function called generateAllReports that accepts a list of these report objects and simply loops through them, confidently calling all three required methods for each report. To summarize today's lesson, the ABC base class makes your class inherently abstract so it cannot be instantiated directly. The @abstract method decorator acts as the enforcer, demanding every child class implement that specific method. And finally, concrete methods allow shared behavior across all children. Together, these elements form what we call the contract. Python strictly enforces this contract, refusing to build any object from a child class that tries to skip a required method. This concludes day 8 and wraps up phase 1 foundations. You have now officially mastered the 4 foundational pillars of object-oriented programming: encapsulation, abstraction, inheritance, and polymorphism.